Very nice introduction. So I'll change the title. I'm going to speak about method and concepts of condensed matter, because that's what the workshop is about, in quantum optics, which is indeed the topic on which I am particularly working now. So I'm going to give you a big overview of the kind of thing that we do. The we, in this case, being my main collaborator, Dr. Elena del Valle at the Universidad Autónoma de Madrid in Spain, and Dr. Zubizarreta Casalangua, who is currently doing a postdoc at the TUM in Munich. And one of the first big ideas that is driving our recent work in quantum optics, which comes from a condensed matter background, is this well-known, well-used approximation, well, not approximation, but decomposition, where you take a field or an operator, in our case, S, and you decompose it into its mean field, so the average value like this, and what is not the mean field, so what we call the quantum fluctuations, that typically are small. They don't have to be small, but the important thing is that this is an operator there, that's an operator there, and there we've got some sort of current state or current field, mean field, if you want. So the total signal is the composition of these two. So that would be the condensed matter big idea that would drive us. As for the quantum optics side, one of the things that we insist very much, which looks trivial when you state it, and I'll show you for particular cases that is not that trivial, is that the role of observation is very important in quantum optics. You shouldn't take it lightly. You should put the observer at the center of the measurement. And more specifically, on top of that, is that there is a lot of things to observe. So classically, we all think in terms of photoluminescence. So here we've got a spectrum, the number of photons that we get from a given frequency. So let's say spectral structure. But if you look at the two-level observable, at the two-photon observable, then you can put your quantum glasses, your goggles. And the important thing is that, in principle, there is no reason why what you see at the two-photon level is connected directly or in an obvious way to what you see at the one-photon level. These things could be independent, right? And because it's quantum mechanical, what is interesting is that the same idea can be extended to any number of photon observable. So you can get your other set of goggles, which look at three-photon observable, and the same thing here, you could have things that are completely disconnected at the three-photon level than they are the two or the one-photon level. And this goes on forever, 4-photon, n-photon. And that's what makes quantum mechanics rich and complex, actually, if you think about it. Quantum computer, what makes it difficult is that what you get at the n-photon level or n-particle level is not connected directly to what you get at the other number of photons. If this is the case, or when it is the case, then we speak of Gaussian state description. For instance, with a few parameters, you capture what happens at all the photon levels. But if you don't have a Gaussian state description, then you need to be mindful to care at a given photon number what your system is doing. So that's another of the leading ideas. So now let's start to go into specifics, because these are general statements, and we'll try to make them concrete and meaningful. So here I put the basic take-home message would be, when you do quantum optics, you should look at the photon where you don't see them, because we always think of photoluminescence. Yeah. But what I'm going to try to convince you is that you should look away from the peaks. That's where the interesting multiphoton physics take place. So now let's go for a particular case. This being the IBS, the Institute of Basic Science, for me is very convenient because I can take the most basic and fundamental system I can think of, which is a two-level system. So I put here a picture of a quantum dot. For us, a two-level system looks something like this. And to start with, we can even look at the most simple possible way to excite the system, incurrent excitation, which means that I will, at a given rate, bring it into excited state. It will emit photons by radioactive recombination. And then, so our observer, the typical observable that we are looking when we think of quantum light.
And what are those two levels in quantum dots? Photon and the exciton, or just two electronic levels?
It could be, yes, the S and the S shape of quantum dots. That's typical two-level system. So it could be an atom, it could be whatever, any two-level system. It could be an atomic transition. So typical observable we are considering is the G2. So you pass your light into a beam splitter, and then you make some coincidence counts, and you get this G2 of tau, the probability density that will be detected with a given time delay. And so far, even though I put this pretty picture of the eye, I didn't put the observer. The observer, at the fundamental level, you can describe it from something that is like an interference filter. That's how the basic level, the theory of photo detection tells you. When you are making the act of observation, you need to bring into your problem the observable that corresponds to the accuracy you have in time or in frequency, the temporal or frequency accuracy, the same thing by Fourier transform, with which you are making your observation. So conceptually, you can think all the time I will be speaking either of detector or filter. It means that we are inserting between our system and our observation, our mathematical observation, the quantitative compute, we are inserting an interference filter. And that describes the process of photon detection. So if we look at the G2 octave of this incrementally excited two-level system I spoke about, so I'm showing here both the theoretical results and some Monte Carlo simulation, we've got this famous result, the textbook result that gives you the anti-bunching. And that's the photoluminescence, so the one-photon observable and the two-photon observable. And when I bring, so far that would be the limit of an ideal detector where I don't take into account this process of photon detection. When I bring my detector into the picture, people at this stage, they basically think that this is a technical problem. It's not something very fundamental. We have a degradation of the anti-bunching because by bringing some photon detection, so some time accuracy, some finite time resolution into the system, what we do is that we degrade a little bit the anti-bunching, and people describe this phenomenologically by saying that, well, you got a qualitative spoil or change on our basic idea. If you do it carefully and you put the detector as part of the theory, what you get is something more complicated of this type. So this type is the exact expression of bringing into the problem of detection of the light emitted by a two-level system, the fact that you need to take into account that it's not an ideal system and it comes with some finite time of frequency resolution. So here I'm showing you what happens if we change this parameter, which is the spectral width of our detector, and we've got thermalization of the light. So that's all very basic because so nobody would be impressed by that because that's the increment two-level system. So to make it more interesting, let's turn to something more complex, which is the current excitation. So this time my two-level system, I drive it with a laser. And that brings us to the physics of the Molo triplets, or the famous dressed-atom representation of quantum energy. So that looks a bit like a polaritons, right? That's the dressing of the two-level system by the laser. We could say that that brings you your upper and lower polaritons from one manifold of excitation. And if you look at the transition from these two polaritons to the manifold below, we've got four possible things. Two of these transitions are degenerate. So in the spectral shape, that gives you this famous Molo resonance fluorescence spectrum in terms of the triplet. Yeah, I guess that this is familiar for most people. So that's one photon physics. If you want to do two photon physics, we can look at two photon transition in these structural level structures. And then from this picture, we've got beautiful things. So either positive correlations or anti-correlations. So for instance, on this picture, you can expect that the side peaks would be anti-bulge because if you got one transition that gives you this left peak there, then you cannot make another time, a second time this transition. You could make one in a cascade, but so the side peak would be anti-bulge in this nice picture. And this has indeed been theorized and predicted a long time ago. That's how quantum optics started with people, quantum so and so forth, predicting anti-bunching from the emission of this two-level system under current excitation. And the state of the art, basically, before, I don't want to describe myself as the state of the art, of course, but before I input, the theory is to make the most advanced, the best description of this type of correlations in the Molo triplet was this gentleman, Gilbert Mingwis, and he has some papers where he shows, for instance, that he brought some quantum mechanical effects like the wish path indeterminacy. There is interference of the two ways the system can go from one system to the other, as a result of which he predicted in the G2 of this resonance fluorescence. So if you put a filter there or a detector to look at the correlation of this peak in particular, he predicted things of this type, that the satellite peak, as I said, at -2 and 2 should be anti-bulge. That's what you get there. That's the G2 of this side peak, should be anti-bulge. The central peak or around the central peak, because of this indeterminacy on the other hand, should be not correlated. So that was the prediction that he made. That's for autocorrelation. You can look at cross-correlation as well. So you start your detector with one frequency, you stop it with the other frequency, and you look at the temporal distribution, histogram of time delay of that, and you get a G2 that he predicted of this type. So again, as before, no correlation for the central peak, and cross-correlating the two peaks, he was expecting no correlation either, but with some bunching on the sides. And there you see that actually he made an approximation. You can see it from the fact that in between the two peaks, depending on whether you approach the system from the central peak or from the side peak, you've got two different results. Yeah, you've got the zero there, or you get the no correlation there on central peak, or you get the correlation from the side peak. So there is some inconsistency from the fact that he's making an approximation on his picture. This approximation being precisely, as I said at the beginning, this one photon obsession we have when we look at things, right? So that's how I would describe the problem. Yeah. Remove this. I don't think I need it anymore, huh? So I just get rid of it. Give it away between me and the stick. So that's our two-level system. And to describe the correlations between the values frequency, the value peak that we have, if we think in terms of the dressed atom picture, so this picture of quantum energy, we introduce some structures, and we would say, okay, if I want to correlate the side peaks with the higher peak, I could make a correlation of this type. That's the approximation of Nimwis. That's the type of thinking, yeah. And that's good enough if you are looking at the correlation of the peaks, but if you start to look at things that we are not sure where the photons are coming from, because these photons fluctuate, so they are not exactly at the peak, or maybe a bit on the side. Then it becomes unclear whether this photon has been emitted, originates from this transition or this other transition. And the problem can even become even worse, because in principle, these two transitions could even be degenerate, and then it's impossible to attach one frequency to one particular process or transition in the system. So there you don't know what to do. So our point, our theory of photon detection, is that you shouldn't try to bring some internal structure, some dressed atom picture, some state inside the thing, which is artificial. That's mathematical construct. You should really stick to the monolithical quantum object, and indeed don't care what is the origin of the photon, right? You should only care that that's what your detector finds. It finds a quantum of excitation at these frequencies. So the important thing that the information of which photon you detect is a parameter, a C number in the corrector. It doesn't come at the level of the operator. And because that's a fundamental process of detection, on top of the frequency, you need to care as well. You need to have at the deepest level of your theory these frequency correlations or filter with or detector temporal correlation. So this gamma parameter needs to be part of the thing. So in 2012, we wrote a formalism. We developed the formalism published in Physical Review Letter to calculate these quantities exactly without making an approximation. So we need to make the photo detection physical theory of two-photon observables. And if we compare what Nimwis calculated by considering the photons are coming from some process inside dressed atoms, which is in black, I remind you, to the actual exact theory in red, we got such a comparison. So the first thing to see is that the physical picture of Nimwis is not too bad. You see the approximation is quite okay around the peaks. And then we have as a nice surplus, we don't have this inconsistency. Now we are able to go from one case to the other in one single self-consistent curve. So this is quite nice already, but it's not important. What's important is what happens actually in this case for the autocorrelation. In the autocorrelation, if you compare again the Nimwis approximated case to our exact case, we see again, so around the peaks, the agreement is fairly okay. We don't have perfect anti-bunching in the exact theory. We don't have zero, but we got some anti-bunching, so qualitatively it's correct. But more importantly, you see that between the peaks here, something happens. The curve is jumping outside of the picture. And if I put it in log scale, you see it better. We've got two resonances, two big things that happen in between the peaks. And what are these things? To understand the origin of these two resonances, now we can jump completely into the pool of this idea of when considering two-photon observable, not have a prejudice as to the peak, but consider all the photons. So I'm going to correlate all the possible photons, which gives me a landscape of correlations. Yeah? Because now I need one full axis for one photon and another full axis for the second photon. And what I show here, the color code is that in red is bunching. So whenever I take two frequencies, whatever frequencies, so this one and this one, I will be somewhere there, I've got a positive correlation. In blue, it's anti-bunching, anti-correlation, and in white, they are not correlated. And here, you have the first particular case of my general statement that is very important to consider or to distinguish the observation of a one-photon observable with a two-photon observable. This structure is different from this structure. Here you've got a monotriplet if you want as well, but at the two-photon level, your two-photon monotriplet looks admittedly different. In fact, even the structure, yes, you don't have a one-dimensional quantity, you need to look at the landscape, literally landscape of correlation. So conceptually, it's very different. At the two-photon level, the physics is there. It's not there thinking in terms of peak, it's there. So now we can discuss the physics of what are these things, what are these lines, what are these circles. So the lines are very simple, actually. The lines that correspond to what we call the leapfrog process is the direct two-photon transition from one manifold to two manifolds below, jumping over this intermediate line. Yeah? By having a two-photon transition, you leave the quantization constraint, and the sum of when the sum of two frequencies is equal to a constant, then what you get is a line. So that's the reading of this line in the two-photon spectrum. So the two-photon spectrum that we predicted, or we proposed 2012, actually has been measured in the meantime by the group of Andreas Müller in Florida in 2015, and you can compare the very nice quantitative agreement between the experiment and the theory. Okay, so one photon observable, two photon observable. What is very important here, I insist conceptually, is that when you are looking at this and you want to do quantum optics, you are biased by your intuitive classical thinking in thinking, oh, I've got the peaks there, I've got the peaks there, how are they corrected? You shouldn't think in terms of these peaks at all. The physics is not these peaks. The physics actually is outside of the peaks. The physics is there in between the peaks. And why it's important to know that? Because once you know that there is some two-photon physics not in the peaks, you can forget your peaks. They are good for photoluminescence, but not for quantum optics. You can put, for instance, a cavity there. If you put a cavity there, what you will find is, thanks to the percent enhancement of the process, you will get a two-photon emitter. And this is a process device that we proposed and published here in this paper, Nature Photonics, in 2014. Notice that it's called n-photon and not two-photon, because once you understand it happens at the two-photon level, you can easily generate to any number of photons. So that's the two-photon observable. Now, if I put my three-photon goggles, I would get something which I need to look at in a cube, of course, because I need three axes for my three photons. And you get a structure which is more complicated. You will again see some circle, you see this line. And this line, you can understand them at transition involving three photons or actually two-photon cascades of two photons. They are the type of things that you see in the three-photon spectrum. So that's a cut, because of course the three-photon goggle is a complicated object. Here I'm showing you an animation where you see the type of three-photon correlation. So when you think of three-photon physics, you should have these type of things in mind. Forget completely about the monotriplet and things in terms of this very complicated thing. I'm not going to show you a four-photon observable, because then I will need to show you an hypercube, and I will start to be a bit complicated.
Sorry.
Yes.
But in that region of the spectrum, and you're looking at, you have the two-photon emission or three-photon or photons, you have very little photons, right?
Yes.
Number of photons is very small.
Exactly. And there, that's the classical prejudice that is speaking. Yeah, because we think in terms of signals. Actually, I was developing this thing in two, in the group of Jonathan Finlay, and I told them, look between the peaks. There is interesting thing. And he said, yeah, but there's no signal, there's no emission. See, but that's the price of doing quantum optics. You should distinguish quality and quantity. Like if you want the water, it's the one photon observable, or you want the whiskey, which is very little of it, you have to distillate it, you have to look carefully, but it's strongly correlated. The fact that it's strongly correlated, it means that even though the signal is small, you are still able to measure it. Actually, you see this Andreas Müller was not so prejudiced about having the little emission. He did it, and he found these correlations. Because there are very little photons, there are few photons, but whenever there is one emitted, the other is also emitted. So actually, the correlation signal is there. But of course, that's your gut impression. Yeah, I don't have a peak, I don't have any physics. But that's one photon thinking. Okay, I'll carry on with the type of mistake or prejudice we make by forgetting the process of observation in quantum optics, by looking this time at the low driving of my two-level system. So not in the mono triplet regime, but at low excitation. So there is two papers, one by the Adato group, the other by the Carol Diederich group, where they did basically the same thing. They both looked at the anti-bunching of the light that scattered by a laser on the two-level system. And they both saw that it was very coherent. That's the Rayleigh peak, very intense bright peak. They both showed that it was anti-bunch. So having these two properties, anti-bunching and very narrow line shape, they concluded that that's what we get. We get a coherent anti-bunch single photon source. But there again, this is forgetting this principal role of observation, which I'm going to put myself. So we do the same thing as then. We're looking at the anti-bunching, like Monte Carlo simulation, for instance, that's our perfect anti-bunching, the particle picture, or we can look at the one-photon observable, the spectrum. So that's the relay peak, very intense signal. And I'm going to zoom there because what's important is what happens there. That our relay peak, a very intense scattered peak laser on the two-level system, is sitting on the incurrent emission of the two-level system. And that's the perfect playground for this idea I started the talk with, of decomposing the total signal as the sum of the mean field. So the mean field in this case is the very bright coherent part that is scattered by the laser and the two-level system, and the luminescence, the operator. So importantly, this is big and this is small in this case. So if you look at the total population, that's the intensity of the bright peak, huge, the intensity of the quantum fluctuation, small, and then some interference there. Except that the interference in this case is zero, because by construction, you see that the average of these things, if I take the average, it is zero. So actually, this term goes south. And what we have is that the emission of our system is the huge laser, the very negligible, very small incurrent emission, background emission, that gives us the total. So again, classically, you would say, okay, so the system is dominated by that. Okay, and you're thinking in terms of single photon observable. What I have basically is my scattered photon. I get billions of these for one of these. Now let's do the same decomposition, but at the two photon level. So it's also an interference, but this time of 4 terms. One of them is a constant one. And then I've got these 3 terms, 2 of which will be important for me, this I naught, which basically is the quantum statistics of the operator of these fluctuations, right? It looks like a G2, not the same operator, numerator and denominator, but doesn't matter. It's basically a G2. So if this is negative, it is sub-Poissonian. If this is positive, this is a bunching or thermal type of statistics. And then you've got the I2 that describes the squeezing of the thing. So the G2 is the interference of these 4 terms, plus this one, which is not very important. In general, it's important in the middle, but I'm interested in the low driving. Here, that's my axis, the driving, and the high driving. So that's the mono triplet, and that's this Eichler regime of Ataturk and Yederich. And here we've got the decomposition. So this 4 term, 1, 2, 3, plus 1. All these 4 things you can check everywhere. In all the cases, they give exactly 0. 1 plus 0 minus 2 plus 1 is 0, and the same here. But the way these 4 things interfere or add together to give 0 are very different. At the low driving regime, you see that we get perfect anti-bunching, G2 equals 0, even though our fluctuation itself, they are bunch, they are Poissonian. So the system is actually emitting photons many at a time. And we've got the total anti-bunching because actually the effective quantum state that we realize at this low driving is a displaced squeezed thermal state, of which the G2 is 0. That's the Wigner function. So it doesn't look like a displaced squeezed thermal state because the displacement is very small and the electricity is also very small. It looks like a sphere, but it is a tiny, tiny little squeezing that produces this perfect anti-bunching. So this is very important because if you ask people why, when you scatter a two-level system, the light of a two-level system, why it's anti-bunch, they will certainly not tell you, even though the system is actually producing chaotic light, it's because we've got an interference of the photon number. What people have in mind is more this picture at high driving, where it's because we've got a two-level system, and a two-level system you cannot put more than one excitation, so one excitation is anti-bunching. This is true, but at high driving. At low driving, the origin of anti-bunching is very different. So we published this result at the same time, actually, with another group, the group of Mark Fox and Maurice Koenig in Sheffield, that's the two work. And why this is important? So I'm going to show here again the two photon observable and the one photon observable, but trying to look at them at the same time. So which means by putting a detector and including the process of photon detection. So we zoom again at the foot of our thing. I put my observer and I'm showing you the G2 that we detect and the spectrum that we detect for various type of detector. If I take a detector which is better to look at the temporal correlation, or a detector which is better to look at the spectral thing. Keeping in mind that I can do one or the other, of course. So here I'm looking at the case where I've got a huge temporal resolution, big temporal resolution, so I'm able to resolve my perfect anti-bunching, but then my observer, he doesn't see this big relay peak, right? That's in the mathematical structure. What he sees is this thing. It means he doesn't see actually that this is a narrow occurrence signal. He sees a flat thing. What he sees is a good anti-bunching. If I change the spectral resolution, so I'm having, in my photo detection, I'm having less temporal resolution, so I lose the anti-bunching, but then I start to gain some frequency resolution. In which case, I start to be able to resolve my line width, and I even at some point with a detector which is good enough in frequency, I can start to see things like subnatural line width emission. Yeah, I can see that the line width is very narrow. It's more narrow than the natural relative lifetime of my emitter. But the cost of that is that I lost completely the anti-bunching because I'm trying to have good frequency resolution. I don't have enough temporal resolution to see the same thing. And that's basically what the experimental papers reported. That's what they published in PRA, is that by looking at the photon from the relay peak, by filtering them, they saw that it was spoiling the anti-bunching. So what this says, this basically is that this claim, this idea of this early group of Ataturk and Derich, that because you got something which is very narrow when you look in frequency, and it's anti-bunch if you look at the photon statistics, it doesn't mean that you've got a current anti-bunch force. It means that you have one or the other. But if you remember you are doing quantum mechanics and you should look at everything at the same time, then you cannot have them together. Or can you? So that's basically the thing. Yeah? The anti-bunching can be very good, the line width can be very narrow, but either you get this when you look at everything at the same time, or you get this. You don't get this thing together. So interestingly, actually, there's no fundamental reason why you couldn't get these two things together. Yeah, it's not that it has to be either anti-bunch or it has to be spectrally narrow. Plus, you should be careful, you should be mindful of the fact that your observation is letting you see one thing or the other. Because now, if you remember what I was saying, that the G2 is the result of some interference between four things, and you try to see that your laser, your source is coherent, so it's very narrow. So you are going to take a detection that is very accurate in frequencies. So you will mess up with the temporal resolution. And by putting a filter, remember the process of detection is equivalent to a filtering. So by putting a filter, what you are doing basically is that you are disrupting this interference because you are removing part of the incurrent spectrum at the expense of the amount of current emission that you get. So you are spoiling these four things. But if you know that you lose the anti-bunching because you are spoiling this interference, it's easy actually to compensate or to correct for this, right? Because in these four terms, there are things you don't control, like the squeezing of our emission, the Poissonian fluctuation of our emission, but this it's easy to control. It's a number one. And one, in the setup, we can remove the excess of current laser we got by destructive interference, for instance. So we propose this in this paper, we propose this scheme on top of the emission of our system that is coupled to something that is going to resolve in frequency and time to get the G2. We superimpose a fraction of the laser, the driving laser, for stability, so on and so forth, with a good phase and amplitude that will be such that it will restore this perfect anti-bunching. And as a result, we propose that in this paper, we demonstrated that this time it's possible to have the joint, the important word here is joint, at the same time, simultaneously, both the subnatural emission and the perfect anti-bunching. So what was claimed, what was promised, because you see anti-bunching and you see current line width button at the same time, you can actually do it, but you might be mindful that the process of observation is affecting one or the other so that you can correct adequately. Okay. And I illustrated it. I illustrated that on the two-level system driven currently, but this is actually a general statement. It's a general principle that applies on everything. So in this review there, we considered all the possible systems we could think about, like James Cummings, one over two photon observable. When people speak of James Cummings, so that's the emission of the photon in frequencies, and that would be the frequency at which we are driving the that's James Cummings, yeah, the laser. So people think of the polyton, that's the lower polyton, that's the upper polyton, and that's the one photon observable. Okay, at the two photon observable, you also have new lines like this of anti-bunching in blue, and new lines in red. So that would be your two-level system there, for instance. And these lines, they correspond to, so that would be the conventional blockade. Your polyton, you drive them and they are interacting, so they oppose excitation, they push anti-bunching. And that's the unconventional blockade, which is the region in the parameter space where the system is self-consistently, I don't have the external laser, but I've got the cavity. It finds the condition to produce this interference that I showed previously on the resonance fluorescence, where the current part and the current part interfere destructively. So destructive interference or constructive interference, and that provides this picture for the James Cummings thing. So you can do it, well, that's an experimental thing. I wanted to say there that when you don't know that, it's easy to miss the features, right? In this paper where they looked at the photon statistics of the driven two-level system, they cut the window there and then they missed the conventional anti-bunching, which is just outside the experimental window. So you can do it for the James Cummings, you can do it for the politons. It's Polyton workshop, so I put this slide. Sven yesterday he showed a bit of this paper, so I will do it as well. I will show some of the results. So we've got a nice Wolfram Mathematica applet you can download for free and play with the thing and change the parameter and look at the photon statistics of your system. So that's a zoom of that. So that's the polyton system. So lower polyton, that's the new line. So maybe to make sense with what I said, we can compare with James Cummings. So James Cummings and polyton. Okay, so you could say that's infinite interactions, two-level system, and that's finite interaction. And you see the interesting thing, like for instance, this unconventional line here in the James Cummings, which is there, it curves and then it splits. And as a result of the splitting, it even intersects with the conventional anti-bunching. So you've got a nice configuration there where we've got a crossing of two features, the conventional and the unconventional bunching. Actually, that's for strongly interacting polyton. The polyton of Sven don't interact too much, that much. If we look at the type of polyton that Sven has, it's more something like this, right? So it's a very small interaction. So what Sven showed yesterday and what he did in the experiment is to look at the anti-bunching there. That's the toward the polyton blockade because the anti-bunching is very small. But it's very easy in principle to have the strong anti-bunching. Instead of looking at the lower polyton, you should look at the upper polyton. Because at the upper polyton, there is this teaming up of these two features. And I don't go into the detail of this because that would be too complicated. But the basic idea is that in this inset there, you got the anti-bunching that was published by them in this Nature material. It's very, very, very close to 1, 0.99 something, or this order of magnitude. But only looking at the upper polyton, at the over branch there, you see that the anti-bunching now is massive, 4.5, so it's huge. And why it is huge? Because you've got this proximity of the over mechanism, which is this unconventional thing, interference of the mean field of the system, of the cavity, with the active emitter. Now I will show you another more recent variation of the problem, which is an interesting one, which is the same thing, but when there is the tuning. So I've got a two-level system, and I'm not driving the two-level system resonantly, I'm putting the laser on the side, as a result of which the incurrent emission now it doesn't sit on the Dirac peak. Before the Dirac peak was there, and now I can put it on the side just by detuning the thing. So very simple trick. And doing this, it clarifies a lot the physics. So that's how you get the current scattering peak. But actually, you don't get only the peak on the side. What you get is that your incurrent background splits in two. There is an elbow there. And the reason why there is this over satellite peak is the same as I said before, is this two-photon transition from one manifold to two below at the two-photon level. But because they are non-degenerate, you can actually spectrally split them in two. And looking at the two-photon observable, so that's the line I was explaining before, and you see there is this nice circle of anti-bunching. How much time you give me?
5 with questions. 5 minutes.
5 minutes. It's enough.
Let's say 8.
I'll try to do it in 5. So there is this circle, and this circle of anti-bunching, therefore, the reason is the region, again, in the parameter space, where the system finds the condition for the destructive interference between the mean field or the current part, the laser, and the quantum fluctuation, so the luminescence of the system. If you look at the condition where this is realized, that's a circle in this two-photon spectrum thing, which is very nice because quantum mechanics, we like lines that corresponds to transition from one energy to the other. It's much more rare to find conditions that give you things like a circle. So that's typical manifestation of squeezing here. Okay. And in the 4 minutes now that I have left, I want to discuss very quickly the nice recent, published a few months ago, variation of the problem that was done not with the semiconductor quantum dot, but with the atom in this case. So two-level system this time was the atom in this in Germany. What they did is that they look at the correlations of the two peaks, and I told you before, so the anti-bunching, it comes from the interference between the incurrent emission that is split now in two, and the current emission, which is the laser that sits in between. So the beautiful variation is that thanks to the tuning, I can spectrally split the current one, strong, and the incurrent quantum one, which is weak. So what they did themselves is that they put a notch filter, which is more or less selectively removing the laser peak, so they can remove it completely or not at all, to look at what is left. Or you can do, which is what we propose, you can do some destructive interference, you send the laser with the opposite amplitude and phase, and like this you can currently remove the field. And doing this, what they found is the same idea that what we did with Hanschke. With Hanschke in two, we said if you look at the laser photon, then you lose the anti-bunching to go toward the current state. There they did the opposite thing. They removed the laser to look at the incurrent emission, so exactly the perpendicular configuration. And indeed, you got a transition from the anti-bunching, here, this we call 0, to the bunching. Okay, so here that's the statistics of the peak alone. This bunching, if you add the laser, the current, so bunching plus current, it gives you perfect anti-bunching. That's the theory, that's the experiment, shows the same thing. And I'll finish with that. The beautiful thing is that you can look at the autocorrelation, which is what I just showed, or you can look again at the cross correlation, because you've got two peaks, so it's natural to say, okay, how does this peak will start the coincidence measurement, and how does this peak will stop it? So a cross correlation measurement. And doing this, again, so remember, if I'm looking at everything, this would be anti-bunch, including the laser. And if I'm looking only at this, then we've got this bunching. So we've got here 4 variations of the things, so various parameters, as function of driving, pure dephasing, detuning, filter line width. So it doesn't matter. The important thing is that you've got this type of cascade. It's typical G2 of cross correlation of a cascade. No correlation before and then some bunching after, which means that one photon equals the other. What I want to insist, and that would be the final main statement, is that there, because we are filtering the peaks, you might say I'm already excluding anyway my central peak. Yeah, so the peak is not there. That's the reason why I've got some bunching, some cascade, but it's not there because it's been filtered out. But this is not true because the interference filter actually it has the fat tail, so it's still sensitive, it's still sensible a little bit to the presence of this current peak. What you can do instead of filtering it out is to homodyne it out, which means to have a laser to exactly or more cleanly, more strongly suppress this thing. And if you do this, you go from this to this. You see, the only thing that I'm doing is that I'm removing exactly or not the central peak. And look what happens. Look at the transformation from a caterpillar from something which is messy, it's oscillating a lot, it's not clear, everything overlaps, correlations are big, but look at the correlation, they explode. Look how the thing is really clean. So now, just by removing the central peak, we've got basically the perfect clean photon cascade, or irradiated single photon source. One photon equals the other. So again, that's the scattering of the laser of the two-level system. And removing the central peak, you get this very beautiful transformation. So my statement, my big claim, what I'm saying is that it's very important to understand the contribution of this current peak on this day. It's doing a lot, very important at the qualitative level. So again, look at, you go from one case to the other. So I will stop there. I was a bit ambitious and I wanted to let you know about things we are doing now on the correlation of this so-called perfect single photon source, but this I will leave out in the interest of time. And I will just conclude by letting you know that in November this year, we are starting a new consortium with people from La Sapienza in Western Rome, so that's the group of Claudio Canti, the Berloff there for the Polyton people, and then this group of Askitopoulos and Simos Tinsos. We promised the European Union that we are going to study what happens when you interfere optical fields in spatial light modulator with the goal of realizing some photonic machine that does some Ising type of calculation. So we'll have some positions to work with us for this in the next 4 or 5 years or so. So if you are interested, then get in touch because we will be looking for people. With this, I conclude. Thank you, Sven, for your patience. And if there is time for questions, I'll be able to try to attend. Thank you.
Thank you very much. I would be extremely patient and would have given you more time, particularly about the perfect photon source, but I was told to stick to time scale. Questions, please. Thanks for an amazing talk, by the way. So, if not, I would get started, but Alberto?
Yeah, can you make a comment about the importance of the lifetime of the spontaneous emission, lifetime of your two-level system, which role it plays in the observing features? It's better to have like a very long-lived excitations or very short-lived excitations, or manipulated with gravity, or what's the role of this?
So yeah,
you always divide by gamma, right?
Exactly. That's what I it's so simple, the system, that the lifetime for us is the parameter that says between. But there is no particular importance of the lifetime there. The one thing is that in line with the fact that photo detection needs to be put in the theory at the fundamental level, it's important to have lifetime because often you can, okay, so I take a non-dissipative system, but we need the lifetime so that the system will use for that. Insofar as it's meeting them, then there's no particular regime that makes it better.
Is the developed approach, mostly from the first part of the talk, is applicable for only one particle excitation. So we have one particle, and on the first level, second level. And what if these excitations are bosons, and we can accumulate many particles, many excitations that's excite at the level? And what if we can, and what if there is non-linearity and we observe kind of illusion?
Yes. So as I said, these principles are very fundamental. They apply to broad range of things. So this we illustrated with the fact of polarity. We can take a bosonic mode with some weak non-linearity. So this 2T model of anti-bulging of the Polyton blockade. And there you can apply all these ideas and apply fully. So it works there. I mean, the case you're mentioning is this one. Take a bit of time to get there. Okay, but here there is no two-level system. Here it's an harmonic oscillator.
Harmonic oscillator.
Yeah.
I have a related or somehow related question because you started off with measuring particularly widely tuned, right? So we are in the weak coupling regime to say, and you need access to all frequencies. But I mean, we experimentalists put things in the cavities that we get more light out, right? Then I would have immediately a suppression compared to being on resonance. So I would need a broadband cavity, right, to probe all the quantum optics. But you also entered regimes where you have light matter coupling being quite pronounced, right? So can I think of light matter coupling just being an enhancement, kind of not like a filter, but a local enhancement in this regard? Because if you go to James Cummins, you alter really the spectrum, right? So what of the physics persists if I'm still in the weak coupling regime, just enhancing photons, or the other where I have the interaction with the two-level system, to say? I wonder, I mean, just cavity-wise, would I go for a narrow micropillar cavity would filter out just one resonance, essentially? nowadays we study a lot the bullseye cavities, which have 10 MeV bandwidth compared to 1 electron volt or something transition energy. You see, then we can probe much more of the physics while still having proper access to the photons.
Yes. Well, okay. So here first there is all the cases got resonance there. So that's if you make a cut at 0, that's L1 and proper light on resonance. That's the distribution configuration. This is strong coupling because here you see the landmills are very small and it's very large to make the features clear. But there is also physics in the recoupling. I mean, there are endless variation of this. Of course, I can only show what standard more particularly. But and we have more in the paper already. There are lots of variation of the system. So I would say that any system you have in mind, the recoupling, so there is process enhancement. Actually, the process of photo detection is a filter, but the filter itself is also a filter. So putting a cavity acts as a filter. It brings a lot of this physics as well. So any experimental system, only you've got the good mind frames, you know what to look at and what to look at, they think something interesting to look at. So I wouldn't say that it's only for strong coupling case, it's just what exactly is interesting or standard. I wouldn't put any limitation that applies for this particular. It's very general, very broad. If I come back to the beginning of the talk, where I lost too much time probably at the expense of my perfect single-photon source, the statement is really that when you want to look at quantum optics, you should look at landscape of correlations because it's a two-photon thing. You shouldn't think in terms of a photoluminescence spectrum and say I'm going to correlate one peak with the other peak. When you think in these terms already, you throw the baby with the water of the bath. You are losing the physics. Now, if it's a weak coupling, strong coupling, if it's a bosonic mode or harmonic mode or whatever, this doesn't matter. Things in terms of photon correlation landscape at the 2-photon level. And 3-photon level, correlation cubes and this kind.
Any other urgent question? Seems not the case, and thanks, Fabrice, once again.